Welcome to lab this week. We're going to spend some time in MATLAB working on some figures and creating some plots. So this is something that is a very common thing to do within engineering and is really pretty critical in creating good figures to illustrate what's going on in the data. And it's pretty critical, something that I do frequently. Okay, so one thing, just using MATLAB or Octave, there's some useful documentation that I want to show you. And also for this lab, we're going to cover 3 sections. The first 2 are with plots, and the third one is kind of a bonus thing on recursion structures. It's going to be kind of revisiting the friction factor example we've done before and actually coding a recursion structure, a while loop, to solve it, just to give you an idea of, say, what goal seek is doing in the background. Okay, so there's some documentation online. You can just search online for MATLAB and graphics or figures, and you'll be able to find this page. Basically, this is kind of the hub for creating 2D, 3D plots, or really any kind of figures to visualize data and communicate results that you have measured or sampled in some way. So this is pretty helpful. I would just recommend keeping this website open and handy while you're doing the lab in case you run into any issues. In this section of the lab, we're going to take the pedometer data that we worked through last week, and we're just going to put it on a cleaner plot and implement some of the things that we covered in the lecture this week. So the first thing to do will just be to create an M file and put the standard header. In particular, you should, because we're going to be working with figures, it's going to be helpful to close all in general at the top of your script file. You won't necessarily do that every time, but in this case it will be helpful. And to start off, I just want to import the pedometer data. So what I'm going to do, I'm going to go to last week's lab. I'm going to run this file so I can get the data to plot. So pedometer, and you can see now I've got AX, AXL, AXP, and T, which that's the data that we're working with. And I also want to just bring up, this was the data that we plotted last week. So one of these we're going to want to do if you're actually going to present data like this is you want to shift it over and just show the 30 seconds of data of interest. So we'll want to show it from 0 to 30, which is just a minor shift to do, but that's something to keep in mind. And also, you won't want to connect these data points with lines. So we'll show discrete data points that show that we've captured the maximum. All right, so what I need to do now is save that data to I'm going to save that data to a mat file. Yeah, specifically, we're going to need T. I think this needs to be in quotation marks, actually. So we want T, we want AX, AXL, may need AXP as well. So go ahead and save those to the file. Oops. And then you want to copy this to this week's file, or folder, excuse me. So I've copied pedometer into my week 12 folder. And now let's go back to that pedometer plot file. So I'm going to load the data and shift the time. So this should be pretty easy. It's just load pedometer, and then to shift the time, we're just going to find that first value of the vector, and we'll just subtract it from the entire vector. So it's pretty simple. And now we're going to plot the data. And there's a few things, and you'll want to go through the full lab instructions, but there's a few things we'll want to do. So I'm going to assign it a figure number. So f equals figure as I create the figure, and the reason is so that I can save this at the end. So that's why we need to do that. I'm going to name it pedometer. There's a semicolon here because I don't want that number to print to the screen. I'm not particularly interested in the number per se. Okay, so now I'm going to plot the time in the axis or acceleration in the x direction. We're going to plot that data. And I want it to be a solid line with x's on the data points that's black. So I'm just going to test this and make sure that everything is working the way that I think. Okay, so the figure showed up over here, and I've got the data. I've got x's on the data points, so you can kind of see the scatter and the distance that's kind of being traveled on the between each data point. So it's actually not a huge amount of data points, but it's I think probably reasonable for what we're trying to capture. Okay. All right, so next up, I want to see you guys use the hold function. So we're going to hold. I'm not sure why Octave does that. It's trying to suggest what I needed to type, but it was not correct. So now we want to plot the actual peaks. If you remember, AXL is the location in the time and acceleration vectors of the maximums or the peaks that we found. So what I want to do is use that AXL to just show those time elements. I'm going to do the same thing for AX. I want this to be circles, so it'll stand out a bit. I want it to be red, and I'm actually going to change this. I want this to stand out more than the other data. So there are lots of functions like this that you can do. What I'm doing is I'm just going to change that face color. So instead of it being an open circle, I want it to be a solid red circle. I'm going to make the marker size or the size of the circle to be larger. Drag this data over. So now you can see it's very clear that solid red circle, and you can see exactly where they are, and that they're at the peaks of the data. 10 is probably a little bit too big, so I could change that to, say, maybe 8. All right, now we're done with the hold, so we can turn that off. And I want to set the limits from 0 to 30 seconds. Oops. For the range of x. And let's just see how that looks now that I've adjusted the size of the data point. It's a little bit smaller. I think it looks a lot better. It still stands out because it's red on black. And it's small enough where we can see space between each data point. So that looks pretty good. Okay, so a couple more things I want to do. We're not going to go ahead and make this a full-on, we're not going to do everything that we can do for this, but I want to just show, let's just example text. Let's just see how this looks. So I just want to show some text on the plot. You can't really even see it here. Notice when I hit auto scale, it actually scales this back, so it takes off my X limit. You see my text is right there. So what I want to do is I want to show it somewhere on the screen where there's more space. So I'm just going to put it in the top right portion of the screen, or the figure. So we're going to put it in 10 and 30. Actually, 30 should be the x-axis, 10 should be the y-axis. And for the notes, I'm going to do this. I want to show this total step count because that's kind of the main point of this figure. And so this is also just to help you out. When you're working with figures, you have to put text on like this, and it's going to be a string. And so I want to show a number here, so I'm going to use a string concatenation function. or strcat, and then num to string to convert that. So I'm trying to show total number of steps, and that is equal to the length or the rows in my AXL vector. Steps. Okay, let's see if I typed everything correctly without any errors. Hey, that actually worked. Okay, so the problem here is it's outside my graph, but that's generally the location I want it to start at. So there's a couple ways you could do this. One is you could tweak these numbers until you get it where you want it, but that's kind of tedious. So I'm going to do something different. So all of these functions, like this text function, they have lots of options, and you can look them up on in the help. But I went ahead and did that beforehand just so I had it fresh. And so what I'm going to do is I'm going to move this. I'm going to move this to the top right. Yeah, that's good. I'm going to change screens. Oh, it doesn't look good. Let's just do that again. There we go. When I change screens, it messes up the size of the graph. But so now I've got it up here to the top right. That's perfect. It's a little small. So let's adjust that. I went ahead and looked this up earlier as well. Font size. And this is a standard parameter when you're using a text function like this, whether it's for legend or anything else. There we go. That is much bigger. That looks really good. So that shows the data a lot better. You can see that I'm counting the peaks, and my total step count in over 30 seconds is 73. So it's a good way to show the data, and then it's always good to put on a label for these. I'm not going to show the legend because it's really just all axial acceleration data. And then to have a title on the graph as well. So we'll just put those on real quick. So let's see. So we'll do the title first. This is pedometer. That's a long title. We'll see how that looks. Let's just set the font size to make sure. You can tell by the coloring. It's important to make sure you use a single quotation consistently. Okay, got the title on there. I'm going to do the X label, and that's just going to be time in seconds, and then the Y label will be acceleration in meters per second. And then let's turn the grid on just because that's better to look at. Okay, see if that runs without any typos or any issues. Perfect. Okay, acceleration and time are small. Let's just fix that real quick. It'll take more than a minute. I'm just going to go ahead and copy this. And here we go. We've got a title. We have a label in units for time and acceleration. And total steps is listed here. And this is really a pretty good graph. So one last thing that we're going to do is save the file. And this is useful if you're creating figures as part of a report or that's needed for a presentation. It's just easiest to actually save that file. So we're going to use the save as function. And this is all available in the MATLAB help. You just look it up, and it's usually pretty easy to find by either Googling it or using the MATLAB help website to search. So you notice here I have F, which is the figure number, and then I'm putting my name, and it should be PNG for that type of figure, and MATLAB will save it as that type. So you can see it showed up here. I can double click it, and here, let's just look at the two of them side by side. So here is my figure, and here's the printout. So it looks pretty similar. There's some scaling things that apparently happened, but I think that's just an issue with the multiple displays that I'm using and with how Octave scales. So you can see this is the figure, and it really captures everything, all the critical information, and it looks pretty good. So that's all we'll need to do for this portion of the lab. For this second portion of the lab, we're going to create some subplots, and so there's kind of two things that we need to do to get to that point. First, we need to create some plots in general, and then we're going to put them into the subplot. So there's two plots that I'd like you to make. One is an acceleration plot of acceleration data similar to what we just did, and the second is plotting some sound data, just using basically a decibel meter. Both of the sets of data, acceleration and sound, were recorded just on my phone using an app, and it was during landing on an aircraft, because I was just curious what the accelerations were, what kind of G's you experienced during landing. And so that's what we're going to do, and it should be pretty interesting, I hope. And to do this, there's a couple things I want to highlight. One is you need to go get the acceleration data matrix file and the sound data matrix file off D2L. I had it in a CSV file, but I thought it'd save you the trouble. You've already done it once where you've imported it into MATLAB and saved it as a matrix file. I'm not going to make you do it again. So I've got that portion of it done, and we're going to work with this to create some plots. So the first portion of it is to plot the acceleration data, and the way that I'm going to do this is I'm going to have one overarching header file, or not header file, script file. So I'm actually going to create this now, and this is going to be called subplots. Make sure it's plural, because if it's not, it'll mess around with your function that's subplot. And this is going to call in an acceleration data plot and also a sound data plot. I'm going to update this in sound data. So it looks like we're doing good. Okay, so we're going to create a figure. And one thing to note here is you don't want to use the close all here, because since this is going to be a subscript, if you close it, close your figure before you've plotted it, it's going to screw up your subplots. So we're going to start the subplots here, create the figure, and then call this acceleration data plot to run it. So don't do this. That's why I've commented it. I'm just actually going to delete it here. So I don't want you to see that and copy it. So don't do that, although it's generally good practice. In fact, what we're going to do is we'll do it here. Close all, but don't do it in your acceleration data plot. Okay, so this should be a good start. First thing to do is load the data. Didn't hit enter. Apparently hit shift enter. No, it's working. I don't know why it didn't work. I pressed enter, but maybe not hard enough. So load Excel data. And now we're going to actually plot the data. So this is in milliseconds. I'm just going to convert it, or you're going to need to convert it so it displays in a way that makes sense kind of intuitively. And I'm going to take a look at this. Okay, so there's a couple ways to do it. I was going to use a set function, which you can do, but we're gonna kind of follow more what I've covered in the lecture. Just with programming in general, there's usually a couple different ways to do things, at least 2 ways, if not half a dozen. So you generally want to choose the way that's the least amount of coding, or that's the simplest and easiest to follow. So what we're going to do is we're just going to plot the data, and that's not what I want. In this case, I want Excel data plot. And now I've got a figure over here. And what I'm going to do is I'm actually going to to limit this to 30 and 70. So that's about where the landing occurred. So it's the data of interest. So we'll set that 30 to 70. And let's put a legend on there. A X, a Y, a Z. So it's the first time we've done a legend. Just see where it shows up. It showed up in the top right corner. That text is really small. So I'm going to move it over to this corner. And the way that you do that, I didn't write this programming language. I'm not really sure why they do this. We're going to move it to the northwest corner of the figure rather than the top left. So that is how MATLAB people wrote it. Okay, so that figure, that legend moved over. Now the text is small, so I'm going to do the same thing. Font size, I'm going to make it 16. And that didn't work. Okay, so it gave me an error in the legend function, but I don't really want to worry about that because that's not my function. And there's also an error in my function or my script file at line 17, column 1. So there's nothing here to give an error. So it's probably on the previous line, I'm not sure. Just going to try to, okay. It's that text, so I'm going to come back to that. Set the title. Make that nice and big. Make sure to get the spelling correct. X label, and we'll just do time in seconds. This is similar to what we just did on the previous one. Acceleration in meters per second. We'll turn the grid on for that, so we'll make it look a lot better. Okay. So the acceleration data, or the title font size worked, but these labels are real small and the legend is real small. So we'll just adjust that font size. Font size 16. And so now that's bigger, this text is bigger. And the legend is still small, so I'm going to actually pause and try to figure out why I was getting that error. Okay, so it turns out there's something a little unique with the legend function. It's different from your title or X label. So there's a couple ways you can do it. I'm going to just show you one way that I think is easier. So the way the legend function works, it doesn't allow you to just set the font size like it does for the others. But what you can do is, just like we can do with a figure, that legend has a unique kind of number in MATLAB. So we're going to store that. I'm not really interested in what it is. And then we're going to set, so this is kind of part of object-oriented programming, legend is an object, and it has a unique identifier or number that we're assigning to L. So we're going to set a parameter of that object, L. We're going to set that to, now we're going to set the font size parameter to 16. And now it should just run fine. Now the legend's a bit bigger and easier to see, easier to read. And I'm not sure why it does that. It has a scaling issue. But yeah, now I've got title, legend, the axis numbers, and titles. So this is a reasonable figure that we could use in a report. It's got enough information that it's useful. Okay, so now we're going to move on to the next portion of the lab. So picking up where we left off, we had the acceleration data plot file completed. Now we're going to do the sound data plot file, and then we're going to put it into a subplot. So I'm going to actually just copy this and tweak it, and you should be able to do the same pretty easily. And I don't remember offhand what's in this. DB, okay. So in the sound data M file, it's got time in dB. You can open the file and check, but I can just tell you now that's what it is. We're going to keep the same X limit. The legend is going to need to be different. It's really just one thing, so we don't really need a legend if there's only one line on the data. I'm going to take that out. And this is now sound level during landing. Decibels, okay. Now I'm just going to check this to make sure that that builds sound data, that it runs. And I've got a figure that looks pretty good. Okay, so that's pretty easy. So that's one of the brilliant things. Once you have the code, it's really easy to copy and paste and tweak it to plot what you need. So now we can come in and do our subplots. And I think you'll be surprised how easy this is and how easy it looks once we've kind of separated it into two plots. Now to add it, if you remember, use the subplot function. And what I want to do is I want to plot this one on top of the other. Just because that's going to be easier to look at. Maybe I'll just do it both ways so I can show you. So one on top of the other means I'm going to have two rows and one column. And the first one I'm going to plot. So P, if you remember from the lecture notes, this is the P, or the number of the figure or plot. And so we're going to start with the first one. And we're just going to run this file. And now I'm going to do a subplot to, there we go, data plot. So I'm plotting both of these, I'm running both of these script files to plot them, and so the top figure should be acceleration data and the bottom figure should be sound data. Let's see if this runs. Subplot, again make sure it's subplots plural. So the legend didn't turn out that great. What I can do is make this larger, and it still didn't scale that well. It's an issue with the legend, with Octave. There's probably not an easy way to fix it. I'm not too worried about it right now. If you're using MATLAB, this would scale a lot better. You wouldn't have the same issues. But in general, now I've got the plots one on top of the other, and so this is useful because then I can look at and I can say, okay, the acceleration here, it was relatively smooth, and now it gets pretty violent. So this is maybe the start of landing, and this continues to bounce. But this one, so this is near 10 meters per second squared, so I need to change the units of that. I think I messed that up on the previous one. Yeah, acceleration is not in units of meters per second, for the record. And so you can see, because it's around the 9.81 meters per second squared, this is going to be gravity, or the vertical axis. And then since I know it's an airplane landing, it's going to slow down in the kind of forwards and backwards direction. And so that blue is AX, so that must be slowing down. So the acceleration is going negative. And it's a pretty quick drop at the beginning, and it just stays pretty level and slowly, gradually decreases the level of negative acceleration, which makes sense as you land. And you also see the sound level. There's a big spike here with that bounce. And then another one as well. And it just kind of generally increases. And then as the acceleration required to brake is lower, the sound level decreases. So if you've been on an airplane, you know that the engines get pretty loud during landing because they're used to, and the brakes are used to slow you down. So I just want to show you real fast. I just think this is kind of interesting. If you instead do them next to each other, and then go ahead and run this, the plots aren't nearly as interesting to look at next to each other. It's a lot easier because you can kind of see what's going on if you have it kind of spread out, so it's the time is longer and they're one on top of the other, so you can kind of correlate. Right now it's like, okay, there's something going on here. Does it correlate with the left side? It's hard to tell. So that's why it's better to have the plot, in this case, for showing the data like this. So it's spread out, you can kind of see the peaks and valleys, and that's one of the things you'll notice if you ever end up doing something similar to this. When you analyze data, a lot of times the scale at which you're looking at the data can make a big difference in understanding and interpreting the data. But that's free. At this point, you have everything you need to code the lab and complete it. So please let me know if you have any questions or run into any issues with the lab. So this next example I decided to add in after doing the first two sections of this lab, just because it wasn't that long for me to kind of walk through and give the tutorial. So I think you'll have a little bit more time, and I thought this would be an interesting and useful example for you. So this is, as I mentioned previously, going to be implementing that same Colebrook-White equation to calculate the friction factor, and we're going to write our own recursion structure to do this. And a very crude method of kind of numerical optimization, just because that's not really the point of this course, but I just wanted to show, because it's a very common thing to do within engineering calculations, is to have a numerical optimization. So just wanted to kind of give you an idea of the iterative process that you can go through to solve for something like the friction factor. For the fourth and final section of this lab, I'd like to revisit the Colebrook-White equation and the friction factor calculation that we did in Excel. So I'd like you to write a script with friction factor as a title, and we're going to numerically solve the Colebrook-White equation. So one of the more common uses of a while loop, because you don't know how many iterations it will take to solve, is numerical optimization or solutions. So I don't expect you to have a deep understanding of that at this point, but I think it's a good example to code for a while loop. So I've got some of the key elements of the code here on the right to show you. The reason I think this is a good example, again, so this is a very complex chart for actually looking at what the friction factor is for a given pipe with specified relative pipe roughness. So, and here's the equation, the Colebrook-White equation that approximates the chart and can be used instead of having to read the chart. So we're going to actually program this, and I'll walk you through a few tips to do this on the next slide. The first thing I'd like to show you is how to actually input data in MATLAB. So we're going to input some data to the variable x. So you use the input function. You can type some text to display as a prompt. Data to be stored in x. So now it displays that text, enter data to be stored in x. And I'm going to type 5, and that is the result. So maybe what you'd want to do is use the new line character, so when you type 5 it shows up on the next line. So now I type 5, and because I don't have a semicolon, the output's not suppressed, so it then spits out the result, x equals 5. So this is part of what I want you to do for this lab. So for the purpose of the lab, I'm just going to define some initial values of the pipe relative roughness, the Reynolds number, and the friction factor. So the friction factor here is going to be, that's the initial value that we're going to start with for our numeric solution. So I'm just going to start the way that I would code this. So I'm going to define a variable here to be called ERR for the error of the numerical solution. And basically while that value is greater than 0.001, which is a typical value for a numeric solution, I'm going to continue iterating through the while loop. So I'm going to initialize this at 1. And when you hit enter, it's going to give you the rest of the while loop. I also want to keep track of the count. Iteration count I equals I plus 1. So I'm going to start I up here equal to 0 to initialize that. So I want to know how many iterations it takes to go through this. And now I'm going to Colebrook-White. So I'm going to calculate the Colebrook-White equation, and I'm going to do the left and the right side. And then I'm going to define the error as the difference between the two. So this is similar to what we did in Excel. And this is the part that I'm not going to expect you to come up with yourself, and honestly this is a very crude numeric optimization. There's much better methods that are more efficient, but this method is going to be reasonable. So if you just have the friction factor plus the error divided by 100, it's going to be reasonable for this range of numbers. If you play with the numbers a bit, you'll see that it may take up to 50 iterations to complete, which is for this equation, it's very inefficient. So there's better methods, but I think this is a good example. So if you have this code for your while loop, I've got the initialization of F, the friction factor, great. And also, one thing that's useful is to know how long it takes. I'm going to put talk here at the end. And I just want to show you how this runs in general. But just note that your code is going to need more information than what I'm showing here. So friction factor. So I didn't see anything results printed to screen because I wasn't showing any, but it did complete, as I can see this symbol here, the two greater than symbols. So I'm just going to look through and see how everything turned out. So error should be less than 0.001, and it is. F is 0.0385, which seems reasonable. The number of iterations is 37. The time it took was a fraction of a second. So that's really pretty reasonable. With a better numeric optimization, you could do it in fewer iterations. A couple things to note here is that that error, the difference between the left and right sides of the equation, can be negative, and so it's easiest just to make it the absolute value. So you want to make sure that there's a couple ways you could write it, but this is the simplest to write that expression. You just take the absolute value being less than 0.001 is when you're calling it accurate enough. And there you have it. That's a good example of a while loop. That's often when this type of loop would be used, would be for numeric optimization, because you don't know how many iterations it'll take. So for example, I'm going to change a few things and see how it changes. And run through my results again. So the friction factor is different, it's a little bit higher. Iterations was 97, so this is showing it's not very efficient. the time was significantly higher, but still a fraction of a second. So that's just, I think, a good example here. And make sure you read the requirements for this problem, because there's going to be a few extra things I'd like you to do other than just get the while loop to function.